So while we had a real world weak base last time, I'm going to share my screen here with you on my iPad, which just takes a second to get set up. Okay, so this is problem 11-23. And let me get you guys up to so I can see all of you. There we go. I'm close, getting there. Okay. So this is problem 11-23. In this case, we're looking at just a hypothetical weak base or a dibasic compound, capital letter B. We're given some PKBs, PKB1 and 2. We're told that it's going to be titrated with a strong acid, hydrochloric acid, and we're given some concentrations and volumes, just like in the previous problem. And then we're told to find the pH at the following volumes of acid, and then make a graph like we did last time. So it's really the same type of problem. I just wanted to do it from the other pH extreme, taking a look at a base instead of an acid. So tell me, what do we do? How do we, let's kind of go through, at least verbally, how we're going to set the problem up and do the first kind of initial portion together. And then I think there's 10 of you today, and it turns out there's exactly 10 volumes. So I'll have you each take one and solve for it, and then you'll walk us through how you did it, and hopefully we'll see some of them done right, and hopefully, well, maybe not hopefully some of them done wrong, but hopefully we'll see some good questions coming out of it to address any lingering uncertainty or misunderstandings. So how do we set the problem up?
Make your little line graph thing.
Okay, we could make a little line graph. You can go ahead and do that. I'm not going to start showing you what I did for a minute because that's not what I did first, but it's fine to do it first. I just don't want to show you what I did first.
Then we could find the volume at equilibrium.
Okay, we could solve for volume at equilibrium or at the equivalence point.
Yeah, that.
Okay. That sounds like a good idea. How would we set that up?
Figure out how many moles of base we have first.
Okay, how many moles of base? So remember, this is just like, I don't know, chapter 5 or 6 or something like that from Gen Chem 1. So a little bit of stoichiometry. I'll show you the calculation in a second. Try to set it up yourself. Take a look at the values you have from the problem. Remember, if it's something you're struggling with, you know, go through and just pull values out. Write them out on the piece of paper. Write down information. Always a good place to start if you're not sure what to do. Okay. Give me a thumbs up when you think you have the equivalence volume 1, and then I'll kind of show you how I set up the beginning of the problem. We'll verify. Okay, is everybody there? The volume that you're getting, do you feel confident in it based on the volumes that we're going to be solving for? That should be a positive reinforcement for you, very positive reinforcement, right? So let's take a look at how I set up the problem here. I underlined some things. Oftentimes when I'm doing base chemistry, starting with the base instead of the acid, I just like to remind myself of the balanced chemical reactions because it can be just a little tricky to reframe how we understand those. It's not simply the opposite, right? We have to produce hydroxide. Then I did exactly what you guys are doing here, where I solved for the volume at the first equivalence point. Stoichiometrically, as Corbin pointed out, I started out with the volume and the concentration of our base. Then we add in the mole ratio for our strong acid. Since we're solving for the first equivalence volume, it's just 1-to-1. We're really just putting that in there so that we can go through and use our units properly and confirm that we're getting the right answer. We're just trying to use dimensional analysis correctly. Then the concentration of that acid is 1 molar, so it doesn't actually change the numeric outcome. We end up with 10 milliliters for our equivalence volume 1. From here, we can draw our number line, right? So some of you may have already done that. If you haven't, go ahead, draw a number line. I put some thought into mine. I saw that the final volume is 22 milliliters. So I just put that as the final point, helping me frame my problem and sort of what the objective is. Then we can label equivalence volume 1 and 2 at 10 and 20. We can label KB1 and KB2. Again, a good reminder that, we're doing a base problem here. We're not talking about KAs. We're going to have to, previous knowledge tells us we're going to have to solve for a KA at some point and use it. But for this point, from this point on, anyway, we're going to be using KBs to start with. It's easy to accidentally go back and use KAs. I've done it myself and worked myself into a mess. So as much as we can, we just want to keep straight. This is a base, not an acid. Okay, then I continued on here and just made a list of the various volumes. You'll notice up top too where the volumes are listed in the problem. I circled all of the volumes that find themselves already listed on my number line, because those are ones that sort of have special ways to solve for them, right? In particular, our K values and our equivalence volumes have very special ways, but also our initial and our final. Now, I think we've lost Brant, I think. I don't think he made it back on. He was having issues with his internet. So I think we're down, let me verify this, but I think we're down to, 9 of you. All right, so here's what we're gonna do. I am going to solve for the pH because I need to be one of you for this problem. I'm gonna solve for the pH at 5 milliliters. I'm gonna take the hardest of all of them and do 5. And now I have you listed here. It lists your videos in the order you joined the lecture. So I'm gonna let you choose a volume in the order that you joined our lecture video. So Brenna, choose your volume.
I'll do 0, please.
Okay, Brenna's got 0. Corbin.
I can just do 1, that's fine.
1. Andrew.
Sorry, I'll do 20.
Okay, 20. Fisher.
I'll do 22.
22. Mina.
Sorry, I'll do 9.
9. Ethan.
I'll do 10.
10. Laura.
15. Is it still left?
I think that's still available. I have not been checking them off, but I think that sounds good. Kenny.
What's left?
I don't think anybody's claimed 22. I'm
Okay.
not sure anybody's claimed 1 either. Anybody claimed 1?
I don't think
Oh,
19.
11 and 19 are still open.
11 and 19.
Okay, I'll do 11.
Okay. That means, John, you're left with 19.
All right.
All right. I'll
We'll
give
be-
everybody a couple minutes and then we're going to walk through. I want you to be able to describe the method sort of verbally and give us a rundown of how you did it and then the answer.
I'm also able to hear now, so.
Oh, so that means that you are taking the one that I was doing. You're going to solve for the pH at 5 milliliters. Can you see it or only hear it?
I can see it and hear it. It forced through an update, and when I opened up the program, it was just
Oh.
not working.
Okay, can you see my iPad screen too?
Yep.
Okay, so you'll do 5 milliliters. That's the one that I had chosen for myself in your absence. take another minute or so if you can, and we'll take a look at it together. Okay. Everybody good to go? Anybody not? All right, hearing nobody object, let's just start then with 0, and we'll work our way through in numeric order.
Sounds great. So I had 0. I'm so nervous about this, and I'm unsure why. Okay. So I started by making a rice table. So I did H2O plus B, the one that you have up right now, for KB1. And then I did 0.01 as my starting of B, and then 0 for BH plus and OH minus. So then I'm getting a K value, I guess, of x squared over 0.01 minus x. And then I set that equal to my PKB1, which is 1 times 10 to the negative 4th. Then I solved for x by ignoring the x in the denominator, and I got x equals 0.001, which would give you a POH of 3 and a pH of 11.
pH of 11, you said?
Yes.
Okay. Let's see. We're very close to that. I'm looking in the back of Harris. I see an 11.49.
That's what I got. The only thing Brenna did, you plugged in the mole amount and not the molar. You took 0.1 times 0.1 liters, but you can't do that for this problem.
Since this is not a Henderson-Hasselbalch, you're actually doing a complete rice table.
Yep. So then, yeah,
Okay.
11.
Oh, my iPad is not updating, is it?
No.
Okay. Oh, now it is. Slowly. I don't know what's going on. I didn't do the math on here. I'm gonna keep track of the method, and then over on the right we'll make our plot as we go through. There we go. Okay. All right, so we said 11.5, right?
Yes.
Okay. All right. Any questions about that one? So we're governed by PKB 1. We set up a rice table. Make sure we put in concentrations. Okay. How about 1 milliliter? Oh,
That's me.
okay.
So what I did is I first found out the moles of the HCl and the moles of base. And then I said some of the base converted into the conjugate acid of it. So I took 0.01 moles of base minus 0.001 moles of HCl to get a new value of 0.009 moles of base.
Okay.
And I used the Henderson-Hasselbalch equation. And for the pKa, I plugged in a value of 10 because you can't plug in your PKB, I believe, Because that would get, well, you could, but I think that would get you your POH instead of your pH.
Sure.
And so then I plugged in a value of 10 because 14 minus 4 is 10.
Okay.
And I did 10 plus the log of 0.009 divided by 0.001 to get 10.95.
That sounds perfect. 10.95. I guess I didn't put my volumes down here on the axis, so we'll go ahead and write in, we have 22. That means we have about 20, which means we've got about 10, 15, 5. So that means 1 is about right there, I think, right? And we're at just below 11. There we go. Okay, any questions about 1? All right, 5.
Pretty simple. Just PKB is 1 is going to be equal to POH. And so then it's just 14 minus 4. You get 10.
Okay. 10. This was at 5, so about there. What's next? 9.
Okay, so I didn't do mine right, but it's before the first equivalence point, so I think you just do it the same as Corbin's.
Yeah. Okay. So here again, it's moles, HCl and B. We take moles of B minus moles of HCl, solve with the Henderson-Hasselbalch equation. We'll just get a different ratio. Same thing we did on the last problem, last class period, right? So now we're talking about 9 milliliters here. What does the pH end up being? You said you didn't do it right. Is that right?
Yeah.
Okay, so Harris shows us that it's 9.05.
I did that one, and that's what I got.
Okay. So there we are. The iPad is updating slowly, but it will update. Let's go on to 10.
Yeah, so what I did is I took the KBs and turned them into KAs, and then put them into the formula to find the hydrogen concentration, the like long one with all the K1s, K2s, and the
Yep.
F. And then I got a pH of 8.
Let's see. 23 looks good. pH of 8. Again, it's just slowly updating. It'll get there. Okay. I don't know why it's going so slow, but it'll add. All right. Next one, what are we at? 11?
Yeah, so after the first equivalence points, we're going to assume that all the deprotonated base is the singly protonated now. And we're
Okay.
basically going to do the same thing that Corbin did, just taking the mole difference, which I actually had the same exact numbers because it was just 1 milliliter added after
Okay.
the equivalence point. And then I actually did the POH way with KB2 and then log of the acid over the base. And then I got a pH of 6.95.
6.95. Looks good. Everybody follow that? That in this case, we're just taking, I wrote on the slide here, excess HCl, but really it's just excess beyond, maybe I should fix that. Excess HCl after VE1, right? And then pH equals 6.95, okay?
I guess I'm confused. So you just flipped putting acid and base in the different locations in your equation,
Yeah, in the Henderson-Hasselbalch.
and that gives you a pH value even if you use a PKB?
That gave me a POH, and then I just jumped
Oh,
to...
I see. Okay.
Sorry.
Yeah.
No, you're good. I just was confused all of a sudden.
And that's, Corbin, what you had suggested when you were going through the problem, right? That you could
Yeah.
solve for the
Well,
POH?
But if you flip your acid and base, doesn't that just change the sign of your log? Do you? I guess
think-
I'm just one. Yeah.
Yeah, so Kenny, explain to us, did you flip the acid and the base and go to a PKB?
Yes, I had the acid be H2B2 plus, right? Because that was 0.009 moles.
So up in the top right of my slide, I wrote a new Henderson-Hasselbalch. Is that what you used?
Yes. Is that right? Or
Yeah, no, I think that's right. You got the right answer, and that's how I would have predicted to rearrange it. You'd leave the plus sign for the log, but inverse the quotient there. And
Why?
then you change to a PKB, I think, right?
Probably. I don't know.
Yep. Notice what we see in the plot as it's developing. It's looking pretty nice, right? We see exactly what we would expect at the equivalence volume. Okay. All right, let's move on to, what's the next one? Is it 15?
Yeah. So for this one, I did basically the same thing as 5, but with PKB2 being equal to POH. So then POH is 8, and then you subtract it from 14 and get a pH of 6.
Okay. pH equals 6, that looks good. Okay, then we're on to 19.
Yeah, so I was not sure how to rearrange the equation, but based off of what we just talked about, I did the same thing that Kenny did, and you come up with a pH of 5.05.
5.05, that's what I have.
Yeah.
So describe
so-
what you did there again for us, because I don't remember which one Kenny did here.
So you're going to set up the Henderson-Hasselbalch, but you're going to do it in a way that you set POH equal to your PKB2 plus log of however much excess acid you have
Okay.
and however many moles of your base are left.
Right, so you're solving for moles of HB plus and HCl after VE1.
Yep.
And then you're using the Henderson-Hasselbalch equation to solve after that.
Yeah, and then you have to, yeah, and that solves for POH, and then you have to subtract 14 and you get your pH.
And you said your pH ended up being, what did we say, 6 exactly?
No, 5.05.
Oh yeah, okay. Okay. 20.
So for this one, we're at the point in which all that is left is the final, it'd be the conjugate acid, which means that we're actually dealing with it acting as an acid. So we first have to change the PKB2 into a pKa, which is just 6. And then using a Rice table, we solve for the X from using the pKa1, which then solving for the concentration of H gives us the final pH of 3.54.
3.54, yep. Sounds great. Okay. And then is it the last one? 22.
So we're after the second equivalence volume, so our pH is determined by excess hydrochloric acid. So you take the volume of the acid minus the equivalence volume divided by the total volume and multiply by the molarity of the acid, and that'll give you your moles of acid, and then you take the negative log, and that's your pH. And I got 1.78.
Okay. Yeah, that's spot on. I wrote there, I condensed your note to, it's basically an M1V1 calculation after you've figured out how much excess HCl there is.
Mm-hmm.
And you said 1.78. About there. Okay. Did I not get the one for 19 written in there? I didn't. 5.05. Let me go back and do that. 19. Okay. So now as we come in and we want to draw the titration curve to connect all the points, notice that initially there's a little bit of a downward slope, a little bit of a curvature, almost like there was a previous, here, let me undo that. It didn't track very nicely for me. There we go. A little bit better there. So we see the two inflection points. We can also see things, you know, the next part of this that we want to make sure we're ready for is identifying our buffering regions. Being able to point out regions on here, for instance, where, you know, we're saying between, this is the territory of KB1. This is the territory of KB2. So being able to overlay onto a titration curve some of the values that we've done on the number lines before when we were talking about predominant species, being able to have all of that combined into one. If you look at your learning objectives, seems to me that one of them related closely with that.
Harris, for the chapter on buffers, like maybe it was chapter 10, he talked about how the buffering capacity for a buffer is 1 pH unit away from its pKa, but here obviously it kind of like goes more. Is that, so like, are you saying the buffering capacity based off of this titration?
Yeah, so we would look at this and we would say, broadly speaking, where I've highlighted in yellow are the buffering regions. More specifically, it is routinely accepted that a pKa or pKb value plus or minus 1 pH unit. So now we're talking about this region here, right? So as I circle this, I'm gonna box in, you'll see it update in a second. You're going to see that it's basically obviously we're eyeballing it. It's still not updating. I don't know why. Let me see if I switch to a new color, if it'll update magically. Well, on the plot there, you'll see some rectangles in a second will show up. And I've basically just drawn the upper bounds roughed in for plus 1 pH unit and minus, here they go, minus 1 pH unit. So that's a little bit more specific based on Harris's description and what's routinely accepted. Does that help? Okay. Any other thoughts or questions about the problem here? All right, should we take a look at homework 6? So it's one problem for homework 6. It says to generate an Excel spreadsheet capable of plotting a titration curve that will be pH versus volume titrant added in milliliters for any diprotic acid-base system in 0.1 pH increments. Also create a plot of alpha functions for each of the 3 species versus volume of titrant added. So it can overlay the same plot. Use Harris for equations and Excel plot formatting. Did I give you a bit more detail in your updated version of it, where to look in the text at all? Okay, so let's take a look at Harris. If you have it available, open it up. We're going to be in chapter 11 here. I'm actually going to close out. Everybody get everything you need off of the iPad screen? All right, let me close that. Let me stop sharing that. We'll go back to, okay. So if we turn into chapter 11, I just want to draw your attention to what's going to be really useful to you, and then you'll have a little bit of time to start taking a look at it. You'll note toward the end of the chapter on page 255. Actually, it starts on page 254. Harris has section 11-10, which is titled Calculating Titration Curves with Spreadsheets. I think you'll find this section of Harris quite useful. In fact, what I'd like for you to do is to plan to set up your Excel spreadsheet with the same general formatting that he has on page 255 in figure 11-13. So up and down column A, you'll notice that he has concentration of acid and base, volume of acid, a Ka value. You'll be adding in Ka1 and Ka2 and a Kw. Just space those out just like that up and down column A. And then what you'll notice is that what might be a little counterintuitive is that you're going to predefine the pHs. So in column B, you're going to just set it up as pH, and you're going to put values in there starting at pH of 0 or 0 point, what I say, a tenth of a pH unit. So you're going to start at say 0 or 0.1 and work your way up to 14. And those values are then going to dictate, in combination with the variables you type in column A, those are going to calculate all the remaining columns. So if you take a look at your pH and then you go to column C in the figure on page 255, notice H+ ion concentration, that's just directly solved from pH, right? No problem. So you can do that one, program those in, use Excel functions to do it, and solve for all of those. Same thing with OH-. What's going to get a little trickier is as you get to column E, F, G, you'll have to add other columns because it's diprotic, remember. Now is when you need to flip to the next page in Harris. This is a table, table 11-5, and it gives all of the equations that you need. Notice that it lays out monoprotic and diprotic. It lays out titrating weak acid with weak base, strong acid, weak base, strong acid, all of those sorts of things. Okay? So what for me, I think took the most time when I was approaching this problem is not really having a great grasp on how to lay out the table in spreadsheet. So just use Harris's general layout and start solving for the different columns. And then your resource as far as functions and equations you're going to need, go to the following page on page 256. Okay?